Okay, good morning everyone. So today we're going to learn about one of the topics in direct current that is called as potential divider. So what is potential divider? Is one way to output a voltage that is a fraction of the supplied voltage. Okay, so let's say you have, for example, you have a phone that is using normally you have 5 volt cable, and then you have a battery that is 9 volts. So you have to convert from 9 volt to 5 volts. This require a potential divider, so it will be a decrease, or it takes a fraction of the 9 volt and goes to the 5 volt. So this is potential divider. Okay, so you need a potential divider circuit to decrease a voltage to one certain voltage that you needed. Okay, so how does the circuit looks? So circuit looks like this. It has a EMF, for instance this one. Okay, so let's say this is 9 volt that I just used for the example just now, and uh, you can have a two resistor, that is resistor number 1 and resistor number 2, and then also you have to output over here. You can use voltage output from the first resistor or output from the second resistor. Okay, so it's only required actually 2 resistor to get the fraction of the voltage from this 9 volt. Okay, so the theory is, since the current flowing through each resistor is the same, thus I equals to V of R effective. So R effective over here is in a series R1 plus R2. So we have I equals to V over R1 plus R2, and R effective is R1 plus R2 because it is series. Okay, because they are in series. So therefore the potential difference voltage across R1 is given by, this is V1. We are getting the value of V1. So figure across R1 is given by V1 equals to I R1. That is V1 equals R1 over R1 over R2. So how does this came to here? You can check the I is actually, you can see that I is equals to I R1 over R2. Remember, in this circuit, we only have one loop only. You cannot have 2 loops. If you have 2 loops, there will be a junction. So there, it requires only one I that is flowing to this loop. Okay, so we continue on. V1 equals to R1 over R1 plus R2 times back with the V over here. V here is the V of the EMF here. Okay. So similarly, the second case means that the second resistor R2 divided by R1 plus R2 times back with the V of the source or V EMF. So 18.26. Resistance R1 and R2 can be replaced by uniform homogeneous wire. Okay, let's say you don't have any resistor, you can replace it with a homogeneous wire. So you can see here L1 and L2, although from A to B is one single wire, you can divide it into 2 parts of wire. Okay, so you just connect one wire. Let's say you have one wire probe over here, one more wire output from here. You can slide its left or slide its right, okay, to get a length that you needed. So L1, L2, okay, is the fraction of the A to B. Okay, wire from A to B. So as we remember, okay, in the previous chapter, okay, as the wire as is longer, the resistance also will be higher. So RAB equals to RAC plus RCB. It goes back to the diagram. R resistor of A to C, or R A to B, R A to B is equals to A to C plus C to B. Okay, So this is what it has here. The total resistance RAB is Y is RAB equals to A to C plus C to B. And R equals to rho L over A, where rho is the resistivity of the wire, L is the length of the wire divided by the A is the cross section of the wire. So RAB rho L1 over A plus rho L2 over A. So here we have, since the current flowing through wire is the same because it's only have one loop, same as before. So I equals to V over R, I equals to V for rho over A, L1 plus L2. So we have V equals to L1 divided by L1 plus L2. Actually, this is the same as the resistor. Remember the resistor R1, R1 plus R2, where V also is the source of the voltage. Okay. So similarly, you have V square, V2 equals to L2 divided by L1 plus L2 times back with V. So note from the Ohm's law, V equals to I rho L over A. So V is directly proportional to the L. Okay. Okay. One example over here is we have, remember this is, it doesn't have two loops. It's only one loop over here. You can see one loop over here. Okay. This is only output coming from the end of the first resistor. This is first resistor. This is second resistor. Okay, only one loop over here. For the circuit in figure 18.34, calculate the output voltage. So we want to find how much is the V over here. If the voltage resistance is 4000 ohm is connected across the output, determine the reading of the voltmeter. So you say that voltmeter over here, we have a voltmeter. This voltmeter also has a 4000 ohm. Okay, so actually if we redraw back, we have the source, this R2, this is R1, and this is connected to the new resistor. So it goes back to the voltmeter. Okay, so this will be the voltmeter. So calculate the output voltage first. A. So R1 is 8000. How did it? R1, yeah. R1 is 8000, R2 is 4000 from this example. Actually, I use R2, this is R1. Never mind, same. The output voltage is given by V out equals to R2 divided by R1 plus R2V equals to V out 4000 divided 8000 plus 4000 times 12. 12 is the source. Okay, so V fraction of the V that taking out from the 12 is only 4 volt. The connection between the voltmeter and 4000 resistor is parallel, so the equivalent resistance is 1 over R equivalent 1 over 4, 1 over 4000 plus 1 over 4000. So R equivalent is 1 over 2000. So remember, this is the source, goes back to the source. This is R2. Okay, so this is R1. So we combine these two resistor, and then we have a new equivalent. So this is a source R1, R2, and goes back to the sources. So this is the new equivalent resistor over here. There. Okay. So hence the new output voltage, it means that how much coming out from here is given by V out equals to 200 divided by 2000 divided by 8000 plus 2000. So now we have 2000. What is happening here? Okay. Okay, so 2000, this is 2000 because it's equivalent to 2000. This is 8000. So 8000 plus 2000 over 8000 plus 200. 2000 times back with the 12. Then you have V out actually coming here is 2.4 volts. Therefore, the reading of the voltmeter is 2.4 volts. Okay. So I'm going to stop here. We're going to give you some of the exercise that use a potential divider. Okay, so see you in the next class. Bye bye.